For those of you who were not here yesterday, do you need the notes for yesterday? Okay, you got, okay, that's it. Okay. We are on the back, I believe, is some color like yellow. And here we go. Okay. So, on a problem like this, it makes it a lot easier if you use analytical geometry, not geometry. Now, that might be difficult if you don't know what analytical geometry means. When I say analytical geometry versus geometry, I'm saying that when you do this question, a rectangle is to be inscribed in a semicircle. To just do some kind of floating circle with a rectangle inside, that's just geometry, right? This is probably bad approach. Instead, use what's called analytical geometry, which is geometry on the coordinate plane, so that you can use equations and all that knowledge you work so hard to acquire in your previous classes. If you put this semicircle on the coordinate plane, well, then everything gets a little easier. For example, if this circle has a radius of 10, then we know that we could write an equation for that circle. Now that it's a circle on the coordinate plane, we have lots of ways to write equations. And furthermore, when I do a rectangle inscribed, rather than call that some nebulous base height, I can use x's and y's, and again, equations. You with me? Makes the problem a lot easier that way. Now, we talked yesterday about the optimization process. The first thing you should do is ask, what am I trying to do? In this case, I'm trying to maximize area of what? The circle or the rectangle?
Rectangle.
Okay, cool. After you do that, now you flow to what's an equation for the area of the rectangle? Now, yeah, base times height is great, but more specifically, what's the base when it's on the coordinate plane? It's, so think of it, yeah, think of it more like 2x, because wouldn't you agree that if you went from 8 to negative 8, then the rectangle would be a base of 16, which is twice the x value? So the base is 2x. That's just an example. Obviously, the rectangle is not going to be negative 8 by 8. It makes no sense. What about the height? Rather than height, think xy. What is it? Y. Okay, cool. All right, so we figured out what we wanted to do. We got an equation. Now what's the problem?
Too many variables.
Yeah, too many variables. Less variables, what can we substitute? Sub another relationship. What's another relationship? What haven't we used at all so far? Yeah, the circle. What's the equation for the circle? Give me any equation and then we'll play with it. All right? That's not what I want. I can't do anything with that. That's terrible. Okay, now we're talking about. Think x and y, please. X squared plus y squared is 100, right? Or y is plus or minus the square root of 100 minus x squared, or just plus? Just plus. We have a semicircle. It's the top half only. It's positive y's. So let's use, in place of y, root 100 minus x squared. You down? Cool. Okay, now, what do I do? That's pre-calculus. Now we do calculus. We want to find a max. A max would be when a prime goes
Positive to negative.
positive to negative. Now, opposed to the derivatives we took yesterday, which were parabolas, super duper easy. This one requires skill. You gotta be on your game to do this derivative. It's a product rule, a chain rule, which is good practice for the test. So product rule, first stays the same. What's the derivative of the second? 1/2 100 minus x squared to the negative 1/2 times negative 2x for the inside derivative. There's first stays the same, derivative the second plus Second stays the same, 100 minus x squared square rooted times the derivative of the first. 2. We want to know where this has critical numbers, which is to say where it's 0 or undefined. You follow me? Okay. With a little cleanup, let's go with 2x and negative 2x in the numerator and 2 root 100 minus x squared in the denominator for the first product. And the second is just 2 root 100 minus x squared. Stop me if you disagree. Okay, the algebra is no walk in the park with your girlfriend here. So what do you do? I was trying to give you a clue there. Get a common denominator, yay! Okay, so 2 root 100 minus x. Actually, do you want to hack it 2? Let's hack it 2, shall we? Okay, so not 2. Instead, just 100 minus x squared square rooted. And here we still have negative 2x squared. And this guy, when you multiply it by the common denominator, root 100 minus x squared over itself, what does it become? 200 minus x squared or 2x squared? 2x squared, yeah? All right, now we're getting somewhere. 200 minus 4x squared over root 100 minus x squared equals 0 or undefined. A prime is undefined if x is what? What would make this undefined? Top zeros or bottom? Bottom zeros, so that's plus or minus 10. Tell me why that's an illogical choice for a base of the rectangle. Yeah, because if you make your base 10 by 10, then you've got that's a minimum area, not a maximum area. You follow? Okay, cool. So let's talk the other. A prime is 0. If 200 minus 4x squared is 0, which implies that 200 is 4x squared, or 50, what do we got there? Yeah, x squared is 50, so x is square root of 50, if I'm doing this right, which is 5 root 2. In terms of a max or a min, I'm not going to make a sign chart, especially for time reasons, but if I talk x's before that, small x's, would this be positive or negative? Positive. And if after that, big x's, this would turn to negative. So is that a max then if the derivative goes positive to negative? All right. Last thing we have to do is make sure we answer the question, what is the maximum area? By finding x equals, did we find the maximum area? No, we need to find the area now. So the area when x is root 50 is, where's the area equation? So this guy, yeah? So we would say something like 2 root 50 times 100 minus root 50 squared, or 50. 2 root 50 times root 50 is 100 units squared. That is the greatest possible area we can get out of this. Are you tracking, people? Cool. I think there's a problem after that. Is it going to take forever? Yes, it will. Skip it. Sorry, we'll have to come back to that some other day. Let's go to 53. Do you have the notes for 53? They're blue? Okay, cool. Okay, the first part is super duper softy, log toss kind of thing. It's using your calculator to evaluate a definite integral. You'll need a graphing calculator out. Get a graphing calculator out, please. Excuse me. Okay, so there are 3 ways to put a definite integral in your calculator. That's the objective for the first part. 3 of them, they're all pretty intuitive. I don't care which one you use. Most students like the last one. I'll show you all. So one way is just to look in the same place we look for all our calculus, which is the menu and the calculus menu. Calculus and the numerical integral is what we're looking for. If you do that, you get a definite integral template. You just type stuff in, cha-cha-cha. You down? Okay. Another place to go is in the catalog of functions button next to the 9. The integral button is right there in the bottom row, second column. There's a definite integral button. You follow? The least amount of keystrokes, however, is just a keystroke shortcut, which is just Shift plus. Shift plus gives you a definite integral, and boom, you're rolling. You down? Okay, so if you go 0 to 2 pi, for example, of sine, I think is what I asked you to do. Is that correct? Just throw that in. Now we could obviously integrate that by hand, so that's silly, but I get something like that, which is not expected, and my calculator is in degrees, so that's a disaster. Okay. Did you get? Did you get 0? Yes, you did. Because what does that say? That says 3.45 times 10. What is e to the negative 15th? Yeah, that means times 10 to the negative 15th power. Now keep in mind your calculator doesn't know calculus. It's not a calculator so much as just a darn good approximator, yeah? As Miss Kenna would say. This, what it's finding is this is almost 0. Tell me why it should be 0, considering the graph of sine from 0 to 2 pi. Yeah, this is all positive area. This is exactly the same negative area. It should be 0. Okay, so obviously, if you write 3.455, you're a total knucklehead who's going to really kick their math teacher off because you were too lazy to move your little eyeballs over 1/2 of an inch to see the scientific notation at the end. The answer is 0. Okay. All right. So now let's talk about how to use this. This is the great stuff. So you should be able to do a definite integral and use it on a problem that's ugly. Now this is the conceptual part that I am adding. The next couple days I'm going to try and get you some AP stuff in ahead of time. Today is the total change theorem, some books call it, or the net change theorem. It's largely word problems, and like I said, it's conceptual. So think through it, and with practice, you'll get better and better at this. The idea of the day is if you integrate a rate of change, then you get amount of change. Integrating a rate of change gives you an amount of change. Why would that be? Well, think about when we did velocity in feet per second. When we did all this area stuff, didn't we do rectangles? And isn't this rectangle base times height? And the height is seconds, and the velocity is feet per second. And so that area represents feet traveled in that time frame. If I said this, no, this rate is actually problems per minute, and I had you find the area under that curve, then you're talking problems per minute times minutes. You get problems. So integrating a rate of change gives you an amount of change. When I say amount of change, you're talking really the amount at a starting time, subtracting the amount at the ending time. That's the change in the amount. Depending on the problem, sometimes you rearrange this. Now just think algebraically here. Maybe they want not so much how much did it change, but where are you now, or how many problems do you have done now? In which case you'd be looking more like what's the amount you have at the end of the change. Now if you were to rearrange this equation here, couldn't I just add this starting amount over? And that would isolate the amount at end. You could also then say the amount after an ending point, at an ending point, is just how much you started with plus how much it changes. Right underneath here, end amount equals start amount plus change, amount of change. That's what the integral finds, is how much
change happened. And so by taking how much it started with and how much it changed by, you get how much it ended at. Some examples. Say f prime is the rate of change in the number of people in the island. Then if I integrate f prime, that is really then f of b minus f of a, or the change in the number of people in the island. F at b represents the people at the end. F at a represents the number of people at the start. If you rearrange this, excuse me, so that you wanted f at b, you could say the people at the end equals people at the start plus the change in population. Same goes with, say, the function f of prime. They give you a rate of decomposition. By integrating a rate of decomposition, I get amount of decomposition. And if I wanted to move stuff around, say I move the f of a over, then doesn't that mean the starting amount plus the amount of decomposition? What would that give you? Starting amount plus amount of decomposition gives you ending amount. Sure. All right, let's look at a problem. And I threw in tons of different pieces that represent all the possible questions here. This is from a HC exam in 2004, but it's fairly common. Not every year, but once every 2 years, even at least, depending on if it's single or double rate. But anyway, so you got this problem here, and it's calculator active. The time frame is from 0 to 31, and they give you a rate of change in the number of mosquitoes on a tropical island at time t days. And there's the function. Now, notice that they don't call it a derivative. They just say this function is R. Okay? But really, because it's a rate of change in the number of mosquitoes, you could also think of it as the derivative of number of mosquitoes. If it's a rate of change, then it would be logically, oh, so this is kind of like R is the same as, n prime, or change in mosquitoes with time. You follow? So, in order to do all this, we'll need this in our calculator. So would you put this function in your calculator and change your window to 0 to 31, please? And I already forgot what it was. So let's see. 5 root t cosine of t. Obviously, we're not going to sweat t. We're just going to use x. And use time, so I don't have an error. And what is it? T x over 5? Okay. Change your window to, at the very least, change the window for x for 0 to 31. And I don't know if I'll need to adjust the Y window. The Y window could probably use a little growing too, yeah? Anybody played with the Y yet? Let's go negative 20 to 20. What do you think, Steph? Oh, yeah, you're right. Maybe I need 30? Okay, by the way, I didn't know this. It's a kind of trial and error, play around with it thing, so your guess is almost as good as mine, maybe not. That was a good call. Negative 30 to 30 is a good window on the Y. Are we down? Okay. Now, we'll get into all the questions here. Let's just think through this. So we got this graph. It'd be great if we actually understood what it means. So what is it? So remind me again, what does this graph represent? Rate of change in the number of mosquitoes. So the y-axis shows rate of change. X-axis shows time. So what's happening in this time frame? The rate is positive, so the amount of mosquitoes must be increasing.
here, the rate is negative, so the amount of mosquitoes must be decreasing, and at the end, increasing, all right? Now, they don't ever ask you to graph the number function. It's just too hard to grade for one thing, but we'll do that later. But I would expect it to maybe, from some starting point, it to grow, shrink, and grow. And we'll get to that in a minute. You got it? Okay, cool. Now, I feel like I understand the problem. Now let's get to the details here. Show the number of mosquitoes is increasing at time equals 6. Now this is one of the hard parts to this is you've been taught so well that you think, well, when I show something's increasing, I take a derivative. So students will always, not always, but many students will think, well, I've been taught well, I'm going to take the derivative. Do I need to take the derivative? Why not? It's already in a form of derivative. It is a rate already. I don't need to take another derivative on it. It's a rate. So do I need to find r prime at 6 or just straight up r at 6? R at 6, right? Now you do need to do evidence. You need to give a calculation, not a, hey, look at my graph. You've got to actually calculate r at 6. So would you calculate r at 6, please? Give me 3 decimals every time. Function of 1 at 6. I'm getting 4.4379, yeah? Okay, so we report our evidence, 4.4379. What does that lead me to conclude? Increasing or decreasing? Increasing, and why? Yeah, this is, so you can actually say that in a sentence after, or you can say, this is greater than 0, so the number, good English would be awesome. So the number of mosquitoes is increasing. What you can't do is leave it to the reader to make the positive conclusion for you. It's not enough to say, hey, it's 4.437, so it's increasing. That leaves it to me to say, oh, it's because it's positive. That's your job to say, because it's positive, that's why it's increasing. You with me? All right. B, at time equals 6. This is where it starts to get wordy. At time equals 6, is the number of mosquitoes increasing at an increasing rate, or is the number of mosquitoes increasing at a decreasing rate? I know it's increasing, but is it increasing at an increasing rate? So isn't that, so what should we do? Yeah, so this is actually would be the second derivative of the number, which would that be the second derivative of r or the first derivative of r? First. Okay, so we need to find r prime at 6. Now if this is calculator active, do I need to go to the equation, bust out the product rule, and show all that? No. You do not. You can just throw it in your calculator, report the answer. So your, so your calculus, your derivative at, what is it, 6? Okay. Of the function, and I'm getting negative 1.9131. You agree? Okay. Negative 1.91. I forgot what I just said. 9131. 9131. So what do we conclude to answer the question? And why? This is less than 0, so the number of mosquitoes is increasing at a decreasing rate. It's increasing because of our previous answer. We know it was increasing from part A, but it's increasing at a decreasing rate. And somebody said the slope of the R graph, and that was true. That's a good point. I don't know if it would pass muster with justification, but isn't it true that because at 6, the slope is negative, that rate is increasing because it's above the axis, but it's decreasing rate because it's sloping down, yeah? You don't want to make allusions to the graph or any kind of comments on the graph in your justification because you're talking gray area there that's hard for them to grade. So you want to use analytical evidence. You good? Okay, go to part C. according to the model, how many mosquitoes will there be? Well, be on the island at time equal 31. Now this is the good stuff of the day. This is the most important stuff of the day. How do you find an amount when you're given a rate of change? Okay, you're going to integrate. Now this goes to those notes we just talked about here. If you want an amount after time, you take a starting point they give you to talk about how much it changed over time. So think in a calculus setting. Actually, I'll give you maybe 30 seconds to write down what you think, calculate, and let's go over it in 30 seconds. Or at least as much time as it takes me to take attendance. Okay. Kelsey, talk to me. What did you do? Okay. So do you agree that, just tell me what's the question? What are we trying to find? Let's get started. The amount at, oops, the amount of mosquitoes at 31. Now, I just used an A at 31. As far as I know, A is not even a thing in the problem, but in my mind, A stands for amount, right? Really, you should say, if you create a variable ever in math, you should, you could call it N, I guess, if you want. And I think I used N earlier. All right, now we just said we can find an amount after time by using the starting amount plus the change. What's the starting amount? All right, so yes, they give you that at the starting time there were 1,000 mosquitoes. Now you can do this in one step or two. You could either write starting amount at time 0 or go straight to the 1,000. Those are both fine. How do we find the amount of change? Yeah, a definite integral, right? That integrating a rate of change gives you an amount of change. What are the limits? From when to when? Why those? Yeah, that's the point you want, and that's the point you need. You want to relate those two. And what am I integrating? R. Do I need to write the whole function? If it's already been named, no. First of all, it incorporates possible copy error. Second, it's a waste of test time. So if it's been named RFT, just call it RFT. You don't need to write the function every time. Let's just before we go on, let's make sure, it's so nebulous and confusing. I want to make sure we're on the right track. So what are the units on that 1,000? Mosquitoes, right? Now go back in the problem and what are the units on R of T? What are the units? Mosquitoes per day. And what are the units on change in time or time? Day. So days drop out. I've got mosquitoes plus mosquitoes. Doesn't that give me mosquitoes, yeah? So do the units seem to track and make sure or make sense that we're doing this well? All right, now, if you put that in your calculator, tell me, what'd you get? A negative? Oh, that's right. 964.335. What would you guess is the most common source of error for students at this school? They overthinking, yeah. It wasn't that it was, they didn't understand the calculus. Oh, they understood the calculus. Because I taught you calculus. What I didn't teach you how to do is round. Yeah. Nor did I teach you how to read. And so make sure that you read. The most common source of error at this school is that people fail to round. It says round. So 964 mosquitoes. Now it's not bad. In fact, I think it's good math to give the decimal answer because you're giving more evidence and then rounding it. I think that's good to do. You don't have to. You can go right to the rounded, but make sure you round. Read the problem. That's definitely something you would underline as you get to it because it got you so many times on my test that by the time you got to the AP, you had that problem worked out and you didn't forget to. Any questions on that?
That is the big idea of the day. Very good. Okay. All right, let's talk about sketching the graph of R. What did we say was going to happen in this graph from 0 till time roughly 7.8-ish, 8-ish? What's happening again? I don't like pronouns. What do you mean it? The number of mosquitoes is increasing, then what? Decreasing till about what? No, you don't need to count it. I'll do it for you. Okay, okay. So 23-ish. Very cool. You said decreasing, then increasing. How do we know how much it increased or decreased? The what? Yeah, the y-axis tells you how fast it was changing, and so doesn't the area then represent how much it changed? And so can we look at the relative areas? So when I say it increases then decreases, is it going to decrease more or increase more? Decrease more. So after it increases then decreases, should I be lower than I started or higher? Lower at this point and then eventually higher. Now these are starting to get hard to eyeball, so don't sweat that. But we're going to pick a starting point. What's the starting point on number of mosquitoes? I keep 1,000. So we're going to start at 1,000. We're going to grow till about when? 7 or 8-ish, okay? Now remember, this is an added problem. This isn't an AP on the AP test because it's so hard to grade these graphs. Then what does it do from 8 to, I think I said 23? It decreases, and we said it decreases more, yeah? So isn't the number of mosquitoes probably less than 1,000 at time 23? Okay, and then what after does it do from 23 to 31? It increases, and that's where we're in some gray area. How much does it increase? Don't worry about it. But as long as your graph shows increasing, decreasing, increasing, always positive. You might think mosquitoes are always negative, but that's a different story. Are you with me? All right. When is there a relative maximum number of mosquitoes? Now, forget this graph, although I guess this graph kind of says this point seems like a relative max, and this point at the end also seems like a relative max because it's at the, really anytime it's at the end of a growth cycle, it's going to reach a maximum, yeah? In terms of the original graph, this is, now remember, this is a rate, so it's like a derivative. When do I see a maximum by a derivative? When the derivative changes positive to negative. So doesn't that also say, oh yeah, at 8, the rate of change is changing from a positive rate of change to a negative rate of change. That's a max. And then, yeah, the endpoints are a totally different ball of wax we'll get to, we haven't got to yet, but at the end of a growth cycle will also be a maximum. So we would say, are you almost out of here? I feel like. Okay, we will, so we get out of here in 2 minutes. We have enough time to at least finish this. At time equal, we're going to need to find that time. It's not going to be enough to say, oh, about this time. So you find that relative max by using what function in your calculator? The zero on this. I don't need to find the max of the rate. That's when it's growing the fastest. I want that 0. So go to the 0 function in analyze graph. And my calculator doesn't do this well. Did you know you can just type in numbers like from 7 to 15 and it'll find it. Did you get 7.853? Okay, so time equals 7.853, and we also said the end point, which was when? Time 31. Why is this a max? Because R goes changes from positive to negative. That's all we're going to get through today. So do me a favor, just keep 52, keep 53. Tomorrow's just catch up day. With me? Okay, cool. Have a wonderful day. If you're really struggling or if you want to work through some of that test practice, I'll be down at the school. Okay? Have a great day. Thank you, thank you.